We're going to move to space, but not yet to the mid-infrared. So even though most of this conference, or all of it, is dedicated to mid-infrared nulling interferometry and observations of Earth-like planets in the mid-infrared, I thought it might still be useful to, for context, to see what might be expected from the visible, optical, UV in space. Especially that we have now the recommendation from the Decadal Survey in the US to develop technology and science and for such a mission with a 6-meter telescope in the future. As we know, when we look at the sun and the Earth from a distance, we can see two components in the Earth spectrum, and they define basically the two ways to go for detecting such planets. One is to go in the mid-infrared, longward of about 4 microns, where the thermal emission of a 300K black body will dominate the spectrum. And that's the one we're going to concentrate in this workshop. And there's another one, which is also to look at reflected starlight at shorter wavelengths. So there, the flux ratio and the dynamic range that you need to obtain is, of course, a lot more daunting by a factor of 1,000. You know, the planet is typically 10 billion times fainter than the star. However, there's been a lot of developments over the last 15, 20 years, both in reference sensing and control, coronagraph technologies, even star shades that make such a mission quite plausible. So here I'm just going to concentrate on telling you what I think, what we think can and cannot be learned from such reflected light observations, specifically in the context of a future 6-meter mission, which for now we call IROUV. The name changes every month, but for now we call it like that. So in terms of science, there's of course many science questions in exoplanet science that can be addressed by such a mission, but for today I will just concentrate on those which directly pertain to small planets, rocky habitable zone planets. So the first one obviously is, are there small Earth-sized exoplanets continuously orbiting in the habitable zones of nearby sun-like stars? We don't really have an answer to that question just yet. Kepler was almost there, but maybe for K stars, but not for F and G stars. Have we ever detected such planets with Kepler? The second question is, are these small planets having habitable conditions? So namely an atmosphere and the presence of water vapor and ideally water oceans. And then the third question is, do any of these planets also display biosignatures, such as the one that Tiffany detailed earlier today, that could be detected remotely? So we don't have like full 6-meter telescope simulations for an IROUV mission. What we do have is the results of pretty end-to-end extensive simulations for two designs which bracket this 6-meter, the 4-meter HEBEX and the 8-meter LUVOIR. So I'm just going to show here some detailed estimates of science field that we got for the HEBEX study for a 4-meter using the latest occurrence rates for different types of planets. These planets are bin by sizes, and for a given size also by temperature. If we just concentrate for now on the Earth-size planets or rocky planets, we expect to detect about 55 of them, spectrally characterize all of them from the UV to 1 micron. This includes 15 in the habitable zone and about 8 Earth-like, so Earth-sized. For the LUVOIR design, these numbers would go up. In particular, they would expect to detect about 28 such habitable zone exo-Earth in the habitable zone. What's interesting is, of course, that these new planets that such a mission would detect occupy a completely different region of parameter space when you look at planet radius versus semi-major axis. These planets are much cooler than the ones that are presently detected by RV and transit methods. They're also cooler than the bright, hot, self-luminous planets that we can detect presently from the ground via direct imaging. And we're going to get spectra of all of these planets. Now focusing on the habitable zone and smaller planets, what's interesting is that such a mission will detect a lot of planets in the vicinity of the theoretical habitable zone region, which is this gray area here, gray shaded area. So not only will we detect planets which are in principle within the theoretical habitable zone, but we'll find a lot of them at smaller or slightly larger separations, slightly larger or smaller sizes, which will provide some nice empirical test of this habitable zone rocky planet concept. There's just one caveat, which is, as we know, in reflected light, we can't really estimate precisely the planet sizes. And that comes from the well-known degeneracy between albedo and planet size. You cannot tell apart a small planet with a high reflectivity from a larger planet with a small albedo. So keep that in mind, because we could detect these planets, but we're not going to be able to derive their sizes or estimate them with high accuracy. That's the type of error bar we're going to get. Next is the ability to find habitable worlds with such a mission. And the mantra here has always been follow the water. Water is one of the few requirements shared by all life on Earth. So this mission will look for broad water vapor absorption features in the near infrared. If you observe from the ground, you know them pretty well because they prevent us from observing in each of these bands here. And we'll also search for exoplanets with global water reservoir with this IROUV mission. That's difficult because the identification of liquid water at the surface can only be done by looking at the dependency of the planetary signal to the illumination phase, both in unpolarized light and polarized light. So here, as an example, our observations actually from the moon, looking back at the Earth at different illumination phases. And what you can see is that the signal that you actually detect is much higher than you would expect from either a pure Lambertian sphere or a planet with vegetation but no oceans. A tough measurement, but probably feasible on some of the planets detected by such a mission. Finally, finding life. So we got to search for biosignatures and place them in context. Here, really the goal is to identify biosignatures in wet Earth-like planets. And we've been using the Sun-Earth system at different times of its history as a benchmark. So what you can see here is that life on Earth, as we've seen, dates back 4 billion years. It was detectable during the Archean Earth through the presence of high methane together with high CO2, which is a strong sign of chemical disequilibrium in the atmosphere, as was mentioned earlier today. And then after the oxygen surge at the beginning of the Proterozoic Earth era, we got now oxygen, which is detectable through oxygen lines or ozone lines in the UV. So the mission will be designed to infer the presence, absence of an atmosphere from the Rayleigh scattering, searching for chlorophyll red edge signature beyond 700 nanometers, and these oxygen and ozone features for modern to Proterozoic Earth-like atmospheres, and also high methane concentrations in the Archean Earth. It's not enough to just find these biosignatures. You also need to make sure that, or at least look for further signs that indeed these biosignatures or these gases were created by biotic processes. So for the case of modern and Proterozoic Earth-like atmosphere, that means looking for the concentration of H2O and oxygen. For instance, if you find very low water vapor concentration and high oxygen, that points to photodissociation of water and differential hydrogen escape at the top of the atmosphere. We'll look also for secondary features which are inconsistent with the abiotic processes and signs of chemical disequilibrium, such as methane. It's going to be hard to detect that at less than 100 times the modern Earth level, though. And same thing for methane. If you find both high methane and high CO2, then you have a strong indication that the methane you've detected was coming from life. All right, then just my last slide as a summary of the promises and limitations of such an IROUV mission for exploring habitable zone rocky planets. So this mission will detect, measure the orbits and spectrally characterize habitable zone rocky planets around the nearest 100 or so sun-like stars. That's what we expect. So FGK stars, mostly, not M. It would detect the presence of an atmosphere as well as water vapor if present at about 10% of the Earth's abundance level over all of Earth's history. It will be able to detect oxygen at modern Earth abundance levels, as well as methane and CO2 at Archean Earth levels. However, it will be challenged to detect oxygen if it was present at much lower concentrations than the current Earth level, because in order to do that, you need to look in the UV for ozone, and it's going to be hard, at least with coronagraphs, to do that. Might be possible, might be a lot easier with a star shade. Anyway, this question mark, I think, here for this type of capabilities. It will also be challenged to get spectral information longward of 3 microns. So we've seen a lot of the methane and CO2 features. The most prominent ones are at longer wavelengths, which will probably not be accessible, at least for most of the planets, given the spatial resolution constraints of a 6-meter telescope. And then finally, and maybe more importantly, such an IROUV mission will not provide planet size estimates to better than a factor of 2, and it will not constrain the planet temperature. And I think Chas now is going to tell us why a mid-infrared mission may do better at that.